Hi everyone. As we get going on what exactly the derivative is and how to calculate the derivative at a point, I don't want us to lose the whole meaning behind this. So remembering that derivatives are slopes, and in the context of any problem, we should be able to figure out what our slope means. So here's one where I don't even give you an equation. I'm not asking you to calculate the derivative. I'm just going to give you some information about a function and the context that we're working in, and I'm going to see if we can figure out what these numbers mean. So we have research coming out of a major car company that gave us a function relating gasoline consumption to the speed that a particular car is traveling, particular model of car. So they've determined that the consumption C in liters per kilometer here, I'll just do this. So this is going to be key, is given by this function C equals f of s, where s is the speed that the car is traveling at, kilometers per hour. Okay, so those units are really good. And one of the first things I like to do in a lot of these interpretations is just really quickly draw axes for myself and say, okay, so this is C is a function of S, and S was speed, which is getting measured in kilometers per hour, and C was consumption, fuel consumption, in liters per kilometer. Okay, so that's the situation I have, and I don't know what it looks like, but I know that's what my variables are. So the first statement we're supposed to figure out the meaning of is f of 90 equals 0.02. So remember, this function inputs an S and outputs a C. So this is telling us, given this speed, we will have this fuel consumption, and then it's just a matter of making sure we tack on our units. So if the car is traveling at 90 kilometers per hour, it should be consuming 0.02 liters per kilometer. So that's what that very first one is. At 90 kilometers per hour, the car consumes 0.02 liters per kilometer. Okay, so that one wasn't a slope, but we're getting there. I think the next one is. The next one is f prime of 90. So this is the same C, but now this 0.0006 is a slope. It's not a C value, it's the slope of a tangent line. So if we were to draw some sort of line in here, we should be thinking about the units on its slope, I think is a good place to get started. So we do a change in y over change in x, which would be liters per kilometer divided by kilometers per hour. So the 90 is still a speed. The car is traveling at 90 kilometers per hour. And the slope is saying that if your speed increases by 1 kilometer per hour, the tangent line predicts that your fuel consumption will increase by about 0.0006 liters per kilometer. So you could say it the way I just said it. Another way you could say that is increasing the speed from 90 to 91 kilometers per hour should cause fuel consumption to increase by about 0.0006 liters per kilometer. So the fuel consumption was 0.02 liters per kilometer. We predicted at 91 kilometers per hour, it's going to be 0.0206 liters per kilometer. So there's a couple different ways to word these. It is good to notice that just like with average rate of change, we didn't want to try and claim that that was perfectly giving us the rate of change of something curved. The same is true with tangent lines. It's supposedly doing a better job, right? It's instantaneous. But still, if something is curved, a line's not going to be a perfect predictor of its behavior. Okay, next one, working a little inverse notation here. So we are supposed to explain the meaning of f inverse of 0.027 equals 100. Okay, so if we're doing f inverse is going to input C's and output S's. So we've just switched things up. So this is going to be the liters per kilometer, fuel consumption in liters per kilometer, and this is going to be the speed in kilometers per hour. So if I am inputting a 0.027, that's my fuel consumption. And if I'm outputting the 100, that's my speed. So this is telling me that the fuel consumption will be 0.027 liters per kilometer when the car is traveling at 100 kilometers per hour. Okay, and then again, back into the slope. So this can be a little bit tricky, but again, if you're keeping track of what's on what axis, I think it's really helpful. So now if we have some sort of tangent line hanging out, it's got some huge positive slope according to this. This is saying if we pick this is now a C value, 0.027, so that's our fuel consumption, same as before. We'll get this slope of 1,428, and the units on that slope will be kilometers per hour per liters per kilometer. So let me see if I can think about this one. If the fuel consumption is 0.027 liters per kilometer, in order to get the fuel consumption to increase by 1 liter per kilometer, notice that's a huge increase, your speed would have to increase by 1,428 kilometers per hour. So this is, if you make this over 1, this is the kilometers per hour, and this is the liters per kilometer. So let me think, what would the other way to say that be? To increase your fuel consumption from 0.027 liters per kilometer to 1.027 liters per kilometer, you'd have to increase your speed by 1,428 kilometers per hour. One way to make that one a little less wacky and unreasonable would be just to, let me think about this, rewrite your fraction. So for example, if we wanted to move our decimal place back over a little bit, we would just have to, what did I move it? 1, 2, 3. Move the bottom decimal as well. And now we could say it as, if your fuel consumption is 0.027 liters per kilometer, to increase that by 0.001 liters per kilometer, you'd have to increase your speed by 1.428 kilometers per hour. So if you like that one a little better, you can do it. All right, so some tricky ones with the inverses, but I really think this helps if you keep track of what's on what axis. It makes it a lot easier to make sense. Thanks for